Okay, let's dive right in. If you're maybe hitting differentiation and integration in college right now, you might be sitting there wondering, okay, great theory, but where does this actually show up?
Yeah, outside the textbook.
Exactly.
Yeah.
So forget the abstract graphs for just a sec. Think about something really fundamental, like a plant, just trying to survive.
Uh-huh. Reaching for the sun.
Right. And its life really depends on water, how it gets it, how it holds on to it, and crucially, how it loses it too.
It's this constant balancing act with hydration, isn't it?
It really is.
And what's kind of amazing is how these math tools, the ones you're learning, are basically the language we use to, well, to understand that balancing act precisely, this deep dive. We're focusing right on evapotranspiration,
Yeah.
which is, essentially water moving from the ground and the plants themselves back up into the air. And figuring that out is, well, it's critical for keeping crops healthy and watered.
So our mission here really is to show how using differentiation, using integration, it's not just homework problems.
Not at all.
It's how we get real, actual insights into this vital natural cycle. You're learning how to measure plants, sort of breathing water out.
Exactly that.
Yeah.
I mean, think about it. If you want to know how fast a field is losing water, like right now,
Okay.
or how that rate of water loss changes, say, during the hottest part of the afternoon,
Yeah.
you're looking at instantaneous rates of change. And that right there is differentiation. You might build a model where the rate depends on things like temperature, humidity, wind,
Great. All those factors.
even the type of plant. And differentiating that model, it tells you how sensitive that water loss rate is to a little change in any of those things.
Okay, so differentiation helps us pinpoint maybe the exact hour water loss is peaking.
Precisely.
Or like how much faster water disappears if the temperature nudges up just 1 degree. It's about seeing the dynamics, the moving parts.
Exactly, the dynamics. And then, well, what if you need the total water lost
Okay.
from that whole field over a whole day or a week or maybe the entire growing season?
Which you definitely need to know if you're irrigating right.
Absolutely. You have to know that for efficient irrigation.
Yeah.
So you're adding up, accumulating all those little instantaneous rates over time.
And that accumulation,
Yeah,
that's integration.
that's integration fundamentally.
Got it.
Yeah.
So differentiation is like the speedometer, how fast, how sensitive.
Yeah.
And integration is like the odometer, the total distance covered, the total water gone.
Well put.
And that tells you directly how much water you need to put back to keep those crops going.
It takes us from just knowing, yeah, water's being lost to actually quantifying how much and knowing when it's happening fastest. These aren't just, curves on a page. They represent actual liters or gallons of water, which is super important for crop yields and managing water resources carefully.
Yeah, what strikes me is
Yeah.
that in the real world, those factors you mentioned, temp, wind, they're not stable.
Ever constant, no.
Yeah, they fluctuate all the time. So calculus, these tools, they let you actually model and handle that complexity,
yeah.
right? You're not just looking at steady conditions.
No, you're analyzing systems that are always shifting, always changing,
Yeah.
which, brings up a point for anyone learning this stuff.
Yeah.
The natural world, and honestly, so many other systems engineering, economics, you name it, they are inherently dynamic, understanding rates of change and total accumulation. It's not just one niche application. It's a fundamental way we look at and manage things.
It really is powerful stuff.
Yeah.
So next time you're tackling a derivative or, wrestling with an integral, maybe picture that field of corn or soybeans, depending on some pretty sophisticated math rooted in exactly what you're learning.
Yeah, these tools aren't just academic hurdles. They're essential skills for dealing with some really big challenges. Food security, water management, understanding climate.
So maybe here's something to chew on then. How many other complex real-world problems are out there? Things like, I don't know, predicting disease spread or designing a more efficient engine. Problems just waiting for you to apply these very same ideas you're working through right now.
They really are the keys, aren't they? For understanding change, for understanding accumulation.
They're everywhere once you learn how to see them.